Good morning, everyone. Thanks so much for joining in with us. Welcome to our topic today, power distribution and dry type transformer testing, differences and best practices. My name is Michael Fleischer, and I'm the America's Marketing Communications Manager for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see an Ask a Question window. You can submit questions at any time during the presentation, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Volney Naranjo, Renewables Business Development Manager. To assist with our question and answer session, we will also have joining us Joseph Aguirre, our Principal Engineer. With that, I'll hand things over to Volney. Thanks so much for joining in today.
Good morning, everybody. Thank you so much, Michael. And well, I moved the slide back to the first one. The topic today is about those little differences or might be big differences when you move on to test from a power transformer, big transformer, high MVAs, to distribution type, pad-mounted transformers. It's pretty much the exact same tests, but there are going to be things that are going to make the testing less efficient or complicate things, or there are probably things that you can do easier sometimes. So that's what the presentation is about today. It's not going to go dive deep into the technical aspect. It's more like about experiences and the typical questions that we get in the technical support group, which I've been at Megger at the technical support group for a while, and I recently moved into the renewables area. In that experience in the technical support group and seeing that in the renewables area, the most typical transformers that you will see are small type transformers, small MVA or kVA sometimes, and well, also related to distribution transformers. So that's the motivation around this presentation. It's going to touch briefly on a lot of aspects, and that's why, or that's how I came up with this agenda. We are going to touch briefly on the testing standards or guides related to transformer testing, just to give a context and a framework. Then looking to have a reference or comparison point, I'm going to talk about the typical testing procedure and the testing highlights of power transformers, just again to have a reference. And sorry, I'm going to turn off my camera so my bandwidth doesn't bother here. So having a reference or related to power transformers, the typical procedure, and again, just putting there some reference and benchmark for that. Then I will talk about pad-mounted transformers, what is different or what you need to consider. A little bit about transformers with OLTC. I guess it's not in the right order here in the agenda because I touched that on power transformers. Then bushings without test tab, and then I move into the dry type transformers, excitation current, transformers with electrostatic shield, short circuit impedance, and turns ratio details. So as you can see, it's a mix of things, and well, I hope you enjoy and feel free to ask all the questions you want, that we will address those at the end of the presentation. So as for the testing standards and guides, well, being this North America, we have, of course, the IEEE guides, and those are the main reference guides. We have C57-1200 and C57-1290 related to liquid immersed transformers or oil insulation. And the first one is the general requirements for the transformer. So it's what the requirements are for transformers, and that includes some testing guides and or testing requirements, and then also the test code that has also a lot of the testing. Uh, there's two documents that replicate exactly the same type of structure of document, but for dry type transformers, the C571201 and C571291. And then there's guide C57152, which is for the field testing, which is probably where we focus the most and where most of the maintenance activities or relates to the maintenance activities. There's also a very good document. It's an excellent reference, Sigrid Technical Brochure 445, Guide for Transformer Maintenance. It has a lot of information and it has a lot of those best practices and things to consider. So those are documents that I will recommend for you to build your maintenance, to build your knowledge, and to have a quick reference on things, specific things. And you're going to see, for example, one thing related to turns ratio that you need to know the document and you need to know that it is there to be able to make to have a transformer pass a result, because otherwise you will fail it. So from the standards, I want to highlight from the field guide, the C57152 table 1. It's a maintenance chart. It's divided in 2 slides here, and it shows the maintenance tests that are available. It's a very comprehensive list of tests. And then it shows in the table at what stage of the life of the transformer it will be recommended, or it is prescribed as needed on the recommended, based on the recommended test results. And there's also optional tests based on the results of the as needed tests. And of course, in some cases, there's not applicable. So here you can see that at a commissioning stage, you have certain tests that are recommended, in-service tests for maintenance, and then for troubleshooting purposes after a trip. An interesting thing here is that there are tests prescribed for a fault in the system, or when there's an actual internal fault inside the transformer. Well, really redundant there, inside and internal, but that's the recommended tests from this standard. And I'm going to be touching about those winding resistance, power factor, bushing testing in this presentation. And this is the continuation of that table. This section talks about load tap changers and the ancillary equipment. That I'm going to talk a little bit about the load tap changer, but not about the ancillary equipment. And then from the Sigrid Technical Brochure 445, it's another interesting table, very helpful in the field and when troubleshooting specifically, because this shows the type of problem, and then it shows what test is recommended to diagnose for that suspected problem. So you can easily find here basic tests, like the typical test that you would have in your toolbox, instruments that you would have easily, that you carry around always for testing, or advanced electrical testing that you may already have those instruments, but you don't use them as much, or things that you may need to ask for some help with an external service, or you need to rent equipment. So very good reference documents to look for information about the tests. Okay, so moving on into the procedure. So typical procedure, you get to a transformer, it has to be de-energized, it has to be isolated, grounds set in place to create the safety area, and terminal disconnection. So it might not be necessary to do the disconnection of the transformer from the conductors of the incoming and the outgoing for some tests, but definitely if you need to troubleshoot or you're doing a very comprehensive set of tests, terminal disconnection is critical. And well, this looking into the highlights of a high MVA or in GSU transformers, big power transformers, of course, doing all of this preparation takes time, and it also takes time to run the test because, well, one thing is to do a quick connection on a transformer that is at your hip height, or another thing to do all of these bucket truck or lift, man lift, or ladder up and down. So it's a lot of time consuming this. You also need to consider your instrument test leads. You need to have a good set of leads that it's going to reach the top of the transformer. And once you're ready, well, there's a bunch of tests that you can run. If we talk about power factor, the traditional method is to do the 60 hertz test and compare the results to a database. Well, if you don't have a database, or if you don't have previous or historic results, then it's very difficult to assess or to make a decision when you have questionable results. So there's a new technique, or power factor is frequency dependent, and there's a very specific frequency that it will give you higher sensitivity. That is testing at 1 hertz. So that is one technique that you can use in transformers, in high MVA transformers, or any transformer. But of course, these are critical transformers. You want to have a very good assessment, and we have a lot of webinars and a lot of information in our website related to this topic. That's why I'm not going deep in this. I just want to put it there as a highlight for you to look into that, or if you need to request more information, gladly we can give you that. And the other aspect about the power factor test, insulation power factor, is that your bushings, you are going to test them as well. They are going to have a test tab or a voltage tab, and depending on the size of the transformer, not only the high voltage side but also the low voltage side bushing. So that adds more test to your routine. And you also do surge arresters, and you also do excitation current. So that definitely you need to have a comprehensive test plan, a test form that will give you all the spaces there for the results, and have everything in one single place. You want to be prepared with that. And if you have several instruments with different software, well, that is going to make your life a little bit more complicated. If you have instruments that can communicate with one single piece of software, or you have a multifunction instrument that can do everything, that is a lot of time savings. That is, and we know that getting a transformer for testing is not easy, and you want to have a good, efficient set of tools. Then something that I just want to mention briefly here, because I have more slides at the end, it's when you run turns ratio, you may get or encounter transformers that are voltage dependent, and you run a test with a regular instrument, and it doesn't get to pass the 0.5% criteria. That might be because of voltage dependence, and a quick solution for that is running the true three-phase ratio meter, using three-phase instrument to be able to get the result. But as I said, this is something I'm going to touch later on in the presentation. Another aspect here is winding resistance. You are going to encounter transformers that are difficult to test for winding resistance, especially Y and D configuration. When you need to test the low voltage side, that's going to demand a lot of current because, well, your current is dividing in it. First of all, you need to use higher current there. Remember, it's 10% of the nominal current that you want to use. And then your current, whatever you're injecting, is dividing through the delta. So really what the current that you're injecting is not going to pass totally through winding that you are testing. So you effectively are testing with less current, the winding that you want to test. So for these, there's techniques that you want to use. For example, dual winding injection, like circulating the current, the same current you're circulating through one winding, you can circulate it through the same through the winding on the other side of that phase. So if you're testing low voltage side, you can circulate the current through the high voltage winding phase, and that's going to give you more flux. Or you can use an instrument that has a dual source to independently energize or test both windings of the same phase at the same time. That will speed up your testing. So that's another technique, and we have also a lot of information on that in our webinars or in our website. Then short circuit impedance, that is a test that, it's a very useful test because you have a value there in your nameplate to compare to very quickly. It tells a lot about the mechanical condition of the transformer, but it's difficult to run. It's difficult to perform depending on the size of the transformer. I have also slides on this specific test, and so I will move on and we'll explain that. If you're testing a high MVA transformer, then very likely you're going to have an OLTC. So when you have this element in a transformer, there are things that are going to change or they're going to be added to your normal testing routine. The very first thing, power factor test, and I start with this one because this is typically the first test that you would run to verify insulation. Well, there's some transformers that your OLTC may need to be in a specific position or not to be in a specific position to be able to be tested. So here I have a screenshot of a manual of an OLTC that recommends not having the transformer on the neutral position, because in that position you're going to have the influence of some resistors, and that is going to add a leakage current. And if you have higher leakage current on your power factor test, then your power factor is going to be elevated. So if you don't know the OLTC, you may end up troubleshooting or not passing the transformer or getting worried about the condition of the transformer without the need of being. So basically the recommendation here is to look at the manufacturer recommendations, take a look to the manual in preparation for the test, or if you're troubleshooting something that doesn't look good on the transformer, then this is one possible source of error. When you do turns ratio and winding resistance, well, that is going to add more tests. You may want to check the entire tap changer at certain stages of the life of the transformer. For sure, at the commissioning, you want to check everything is good. And for maintenance purposes, well, it depends on the practices and the time you have, but the typical test is to test on neutral, and then one raise, one low, and 16 raise and one lower. And sometimes you may want to test on the tap that was found just to verify that it is good. If you know that the transformer, it regulates constantly, you may want to check the tabs that it usually goes through just to see if there's any wear or tear. And then there's a specific test, and I didn't mention that, or I didn't show that specifically in the test, the recommended tests from the tables. But for OLTCs, you could have vibration, you could have dynamic resistance measurement, which is the one that I have here. You can measure the current of the motor. And dynamic resistance measurement is a very comprehensive, because it will look at the stages, the transitions, all of the transitions, and if you have resistors, it will measure the actual resistance, it will measure the timing, and you can see if there's any contact bouncing. So you have a very comprehensive test here for for OLTCs. And then it's a very simple test, but not easy to run sometimes because you need access to the conductor, to the grounding conductor of the core. So every or all the cores in a transformer or transformer cores are always grounded. And if it's a small transformer, well, the conductor will run from anywhere there in the core to the tank, specific point in the tank, and that's how they ground it. In big transformers, as you can see here in my image, well, you have a conductor and it's brought here to this point, and well, it's actually this one. And then you can remove a cover there. You will see a bushing, and you'll see that from that bushing, it is being connected to the tank. So you have an easy access to test the core. It's not typically performed. We always recommend running this test. It's just a matter of opening that grounding connection using an insulation tester, 500 volts, 1 kilovolt, depending on the size of the transformer you could use, and then check if it is grounded. There should be only one ground path or one path to ground in the core. And when you do this test, you find out if there are more connections to ground. And that is something that needs to be fixed, because then it will create circulating currents, increasing temperature losses, and deteriorating or degrading your transformer faster. So it's a very easy test to run and important in your tool or your maintenance program. Well, with this and having established that reference and those highlights, then we move into the topic of the presentation, or more in depth to the topic of the presentation, which is the smaller transformers. So pad-mounted transformers, these are very common, these are very popular, and you will find them in distribution systems everywhere, and of course also in associated to renewables sites. Two type of bushings that we have here in these type of transformers. One is the live front, and the other one is the dead end. Live front is the typical bushing. You can see here porcelain, and then the terminal there for you to connect the conductors. In the dead front, you don't have the actual terminal, the actual conductor exposed. The conductor is deep in the well bushing here, as you can see here in this slide here. So when you have your distribution system connected, it's dead. You could say that you could go and touch this because everything is insulated. Of course, I'm not recommending to do that, but it's dead. So when you get to test, you remove the load break elbow, but then you are left with this bushing that has no access to your terminals. And it may sound silly, but these are actual calls that we get, and sometimes we get to demonstrations, and we get to the transformer, and there's no way to connect because there are no adapters. So that's the bottom line of this slide. You need to have some adapters to test these transformers. For any test that you want to run, turns ratio, winding resistance, short circuit impedance, power factor, you need to have adapters. And here are different solutions. In this picture, this is testing a regulator, a three-phase regulator. And you can see that the user has the actual elbows, load break elbows. He used a set of those to make pigtails there to connect. So he has the conductor at the end of that, the other end of that load break elbow. It has a conductor exposed, and that's where he connects the leads. In our case, we offer for our instruments these load breaks, these adapters. But you can also make them. You can just use a copper well rod And if it is, you need to know exactly what the size or what gauge you need to insert that into the bushing well, and then you have the length enough to connect your leads, as you can see here in this picture. Probably that not very clear, but that's what they used in this case. They used these simple adapters. They made them in-house, let's say. Then the other aspect about pad-mounted transformers that makes it a little bit difficult to test them sometimes, and again, this is coming from calls that we get, uh, that they call and say, hey, we are not getting any result, the instrument is having an issue, or what's going on. So, well, as you can see here from this image, well, the load break elbow connects, and there's definitely the conductor that is going to the winding, but it's associated to a fuse. So pad-mounted transformers very likely are going to have fuses. And you, of course, the first thing is that you may want to check the fuses when you are testing as part of your routine. Second, if you go into more detail here, you can see that there's an isolation link. And then here it shows that goes to a primary winding, but in some other cases, you're going to have, in addition to the bayonet fuses that are accessible to the user, there's additional fuses called current limiting fuses. And well, let's say you are testing and you don't get any signal, a simple test like a turns ratio, and you are applying voltage. If there's no circulation there on the primary side, then you're not going to get any results. So are the fuses good? Are your well, basically the first thing would be, are your adapters well connected? Are your adapters making contact? And then, are your fuses good? Are the fuses there? And finally, you might have these current limiting fuses. And if you read the manuals of the transformers, you're going to find that these current limiting fuses will operate in very high current cases, and they are there to prevent catastrophic failure, but the transformer might be failed, or the fuses might be failed, and those are not accessible. So even though you have good connection, your bayonet fuse is good, then you're not going to have any circulation. So in that case, it's like a call to do an internal inspection of the transformer. One other aspect here I forgot to mention, this isolation link might also be open. It's part of that protection to the transformer, and that could be one of the reasons you don't have any signal going through the transformer. And before I talk about this, you can see here in this nameplate that is indicated in the transformer. So reading the nameplate of the transformer, understanding the nameplate is pretty important for the performance or running your test. You want to be informed about what transformer you are testing, and this is a good. The nameplate gives you a lot of the information you need. Well, the topic of this slide is that mounted transformers, as you can see, they have two high voltage bushing sets, or two sets of high voltage bushings. And this is because pad-mounted transformers, one of the typical applications is for loop feeders. This is a technique to have less users affected by an issue in the system. If there's like a fault in the cable, well, if it's a loop, only one small section of the customers will be affected. So this guarantees the reliability of the system. Well, when you're going to test, ideally you already disconnected. If it's actually connected to a looped circuit, well, ideally you disconnect both feeders, and then if you start, or you may get bad results, for example, in power factor testing, because there's a switch. There's a switch that allows you to select what feeder you want to be in operation. So, for example, for the actual loop, you want feeder A and feeder B to be energized, and there's a position for that. So, in this load break switch, there's a position that will have sides A and B on. Uh, if you leave it like that, you might get leakage current when running power factor testing on this other side. Let's say you are connected to side A and you didn't do anything on side B. You left the conductors or the actual cables there, or you disconnected them, but you didn't do a short, or there's something causing leakage current. You're going to have bad results on the power factor. So it's important to understand these load break. There are other switches, load break switches that will have only two positions, on or off. So that is probably easier. But if you have these four positions, it's important to have an understanding of what position it is, and be aware that having these might introduce you high results on power factor. One more about the pad-mounted transformers is that typically you're going to encounter YN configuration. And the characteristic about these, if you look at these nameplates, you're going to see that the two neutrals from the high side and from the low side are bonded together. You can see exactly that here as well. And here you can see that. So, and typically, those bonds are going to be inside the transformer. So they're not accessible. You're not going to be able to remove them. You can see here that this shows removable link. Let me remove the highlight. So this is a removable link, and even sometimes you see that in the nameplate. It's a removable link, but it is inside the transformer. So when you are going to test, it's not actually possible to remove it unless you go inside the transformer. Well, what is the effect of these, or what is the problem with these? Well, not the problem, but what it causes is that, well, you will have the two windings connected together internally. And for power factor testing purposes, one of the tests that you do when you run power factor is that you do from high to low insulation. So you do the CHL test to see how the insulation is between high and low voltage. Well, the two windings are together, are tied together, so there's no insulation between them. Well, there's insulation, but they have a path to ground, or a path between the two of them through the neutral, and that is not going to give you good results, or it's going to probably trip the instrument when you're running the power factor test. So there's nothing you can do, and as much as you want to test the insulation, the only thing that you can do is to run the test from the high side or from the low side, and just get an insulation measurement from to ground from whatever side you want to test. It's basically the same as testing an auto transformer. And again, these are typical calls we get asking, is my transformer bad? Or my instrument is tripping. What am I doing wrong? Or is the instrument with a problem? So again, read the nameplate, understand what you're testing, understand what you're connecting to, and that will give you a good guidance on what you need to do. Then, if we talk about the live and the bushings, well, those, as different from the high MVA transformers, you're not going to have test taps. And not that you're going to be testing these bushings that frequently, but in some cases you may want to have some troubleshooting tool or something to find out if the bushings are giving you are the culprit of a high power factor result. I'm not going to spend much time here, but I have two slides on a technique to test these bushings. So you will use the hot color test, which is a test that applies a high voltage to the porcelain instead of the conductor of the bushing, and it measures any leakage current to the conductor through the porcelain or through cracks, or let's say the cement bonding the metal to the porcelain, uh, and also to ground. So it measures the leakage, and you actually don't measure the power factor, you measure the leakage current, and the analysis is by trending or comparing the uh, the results. And you have 3 bushings or 4 bushings, or in this case you have 6 bushings that you can compare to. So not that you need a database, you can test always against the other bushings. It's a technique also used to determine the level of oil. So I guess these horizontal ones probably not, unless you have a really bad problem of oil level. But for bushings that are vertical, and they are embedded in the oil, you may want to determine you can determine what is the oil level with the hot color technique. I'm skipping this one because that's related to the analysis. Then with this, I'm done with the pad mounted transformer specific things, and then moving to the dry type transformers. These ones, well, you can see here there's basically two main types of insulation style. Uh, there's the open wound, vacuum pressure impregnated, and vacuum pressure encapsulated. All of these 3 transformer types, they look pretty much similar to this one here, that you can see the actual configuration of the wind, not configuration, but the turns in the winding. You could probably go and count them. It's kind of a nice visual of a transformer because it lets you see everything, as you can see through. The cast iron is this type, the red insulation type, and well, the conductors are there, but everything is inside this cast resin that doesn't let you see the conductor. Now, the highlight here, what I want to mention here is that, well, the vector configuration in the tap changer is actually accessible to anybody. And you can see here how the delta in this transformer is made. And you can see that this other transformer, sorry, I'm not using my pointer here. So you can see the delta being done here for this one. And in this other case, the delta is made different. You can see that the cast resin transformer, it's going from the head of phase A to the tail of phase C, while in this one, the head of phase A is going to the tail of phase B. So you can see that the delta can be done different ways. And the other aspect, I don't know, it might be a little bit small, but you can see a little link here. You can see conductors coming to the center of each phase. And you can see a little link. Basically, this is the tap changer position. So different from oil immersed transformers, now you have, instead of a switch that you just rotate to bring it to position 1, 2, 3, up to 5, or sometimes 7, you have to do an actual manual connection for each phase. And here you don't have the links, but you see the spots to do the connection. So the bottom line here is that you have a configuration that can be easily changed or can be easily messed up, and then you need testing for that. The other aspect is that if there's a Y-type transformer that is designed for dual operation, for delta or Y operation, the standard, one of those documents that I mentioned, says that it needs to be shipped from the factory connected for Y voltage. So if you are commissioning a transformer, that's the first thing that you need to do. If it's going to be operated on delta as a delta, you need to change that connection. It needs to be done properly, and it needs to be verified. And the other aspect about the dry type transformers is that they're sensitive to dust, dirt, or animals. They have open ventilation, and they're well insulated. They're actually good in wet environments. But if the transformer is not operating, it will, because there's no heat, it will accumulate moisture. It will accumulate dust or contamination very easily. Or you could have animals, small insects or small animals, putting or establishing their residence there. So that those things need to be considered when testing the transformer. So TTR is checked. It's used to check. It's the best tool you have to check the configuration, the vector configuration, and the tap changer selection. The modern instruments, turn ratio testers, will have a feature that will do an actual verification of the vector diagram. So if you say it is a delta YN 7 or 5 or 1, it will actually do a verification to confirm that is the actual, that what you are testing is actually that. And then just by running a turns ratio, you will be able to verify your tap selection. When the other aspect is when you do insulation tests, and it could be insulation resistance or power factor. And for dry type transformers, it is more typical and probably better and quicker to use insulation resistance for the assessment of the insulation. However, power factor can also be used. And no matter what you're doing, you need to be aware that because of that exposure to the elements, the test is going to be subject to wide variations in the results. And this is because of the effect on the surface of the transformer, like for the moisture, because of the moisture or the contamination, or if there's any spider web or whatever other animal with something contaminating the surface of the transformer, then it's going to give you bad results. Good thing is that if you dry the transformer, if you clean it, and if you inspect it and have good or best practices there, then you're going to be able to improve the results. Sometimes these transformers have heaters, and if the transformer is de-energized and the heaters do not come on, then that is another way to cause the insulation test to not be good. So always check those things, cleanliness, and the condition, and also their heaters. It's good for them to be checked for when the transformer comes off. Now, if you still get bad results after cleaning and after verifying everything is in good condition, at least visually, then and there's no moisture there, then you're going to that's an indication that there's a problem with the insulation of the transformer. And speaking about power factor, well, it's a little bit different from the oil immersed transformers. There's no specific limit value for oil transformers. We know that 0.5% is down, below 0.5 is good, between 0.5 and 1 is aged or a used transformer. It's might be a normal result, but you might want to keep an eye on that. And if it's above 1, it's an investigate and probably do not energize. So for dry type transformers, we don't have that. There's no specific value because being a dry type or being a dry insulation, the power factor and the insulation resistance is going to be dependent on the voltage. And that's why probably instead of an actual specific power factor result, you want to do a tip-up test where you increment the voltage in 5 steps and not to exceed the nominal voltage, line to neutral. And then you see that the power factor should not be changing or increasing much. So there should be there's going to be a voltage dependence, but it should not be that high. And same for insulation resistance. Insulation resistance testers, they have a testing option or a testing setting that is called step voltage. So for insulation resistance, it's called step voltage. For power factor, it is called tip-up test. But it's pretty much exactly the same concept. And then for power factor, there are no temperature correction tables. Again, it's dry type, it's a different modeling, it's a different behavior, and the standard mentions that there's no correction tables and that you should try to test always at the same temperature. So in that sense, it's probably good to have the heaters in operation before running the test. So you try to bring the transformer to a stable temperature and always test at the same temperature. Okay, moving on. Another characteristic that you could find in small type transformers, it doesn't matter if it's dry type or oil immersed transformers, it's about the excitation current. Here you can see in this table different transformers, different voltages. All the blue shaded transformers are of a certain voltage, high voltage. There's just one small transformer that is not that on the high side, but all the other are on the high side transformers, high voltage side. Not extremely high, but they're just the typical distribution transformers, certain MVAs, a good MVA range. And you can see that the excitation currents are low. So typically, big transformers will have low excitation currents. And of course, I'm just showing like the average of the three phases or showing that probably the highest value of all the phases of the three phases, but you can see it's low. Then in the orange shaded section, you have the low end of the medium voltage, and you have low MVAs, and then you can see that the excitation current it's quite high, and even though it's already at a reduced test voltage. So the highlight here is that small transformers very, very likely are going to have a high excitation current. Excitation current depends on the quality of the transformer, the core condition, the core construction, a lot of aspects, and also it's related to the efficiency. So distribution transformer might not be the focus for having a very efficient transformer. So that's probably one reason to have a high excitation current. And a typical call we get is, okay, I'm running an excitation test and my instrument is tripping. So the instrument is having a problem, or is my transformer with a problem? Well, what is the excitation current you're getting? I'm not getting it because it's tripping. Okay, let's reduce the voltage. And then you can see that at 5 kV, it's already 119. And this is a 13.8 transformer that can be tested up to, not to exceed line to neutral. So that will be somewhere around 7,000 volts. So this transformer very likely couldn't test at 7 kV because it will trip the instrument. Power factor instruments typically have up to 300 milliamps of current, and there are some that can have up to 500 milliamps. So it's a characteristic of the transformer. So you need to lower your voltage, and the most important thing here is to be consistent, because excitation current is a trending test. So you want to be consistent to be able to compare results in the future, because excitation current is voltage dependent. Okay. Then we have transformers with electrostatic shield. We have situations in which the transformer is connected to a system that probably sees a lot of noise on one of its sides, and that it's not desired for that noise, that interference, uh, high frequency signals to go to the other side of the transformer. So they installed an electrostatic shield, and it works perfectly for the normal operation of the transformer. But when you want to run a power factor test to assess the insulation, it will give you bad results on that CHL, that insulation measurement between the high and the low side. So uh, you have no option other than just testing from the winding side, from the high side, or from the low side to ground. But you're not going to be able to assess the insulation between the two windings. Uh, that's something that's how it is. That's what it is, and then probably the only option that you have to verify the condition of the insulation of that transformer to get another insight is to run a DGA test. And if it's a critical transformer, probably you want to add a monitoring device to check a couple of gases and to check moisture. Then, not related to electrostatic shields, but you may encounter some transformers that you test and power factor is bad, and when you check at the capacitance, it is very low. So there are transformers that have very low capacitance. These are just a few cases we have seen, but if transformer has a very low capacitance, it's going to be difficult to be tested for power factor because of the currents are going to be affected, and it's not going to be much current there to measure, so it's difficult to measure. Okay. Going back to the short circuit impedance that I started before, that I mentioned. So again, it's a very good test that verifies the winding and the core, the mechanical condition of these two parts of the transformer. Once the transformer is built, nothing moves, and the distances and the separations are fixed, and that creates a very specific and characteristic impedance. Because it's a circuit, and if the circuit doesn't change in its geometric configuration, it won't change in its electrical parameters. So it's something that you can always measure and should be the same. And well, it will change if there's a fault or something that causes a deformation in the transformer. So transportation, high current during faults, or seismic activity, or actual degradation of the transformer. When transformer starts degrading, the structure kind of gets loose, and that is probably going to affect also your short circuit impedance value. And this is a value because it's fixed. It's something that it's displayed in the nameplate, and you can measure easily. And compared to that, now it is in the concept is pretty easy. You apply a voltage on the primary side with the secondary side shorted, and then you get the current and you get the voltage, and from that you can get the impedance. However, this source needs to be a source with a certain amount of it needs to be powerful. Not that you need a generator, but you need a source that can give you a good amount of current at 240 volts or 120 volts, but give you good 10 amps. So it's a powerful source that makes instruments heavy or make the test probably not so safe. And then the other aspect is running this short. Here you can see two pictures. This first short is done by hand with just a shorting link or a shorting cable, and this other one is made with a good bar and a good connection, probably torque. So definitely a test that is run with these two type of shortings or shorts, it's going to give you different results, and this is what makes the test difficult in the field. And the other aspect is that if you are not careful, you could leave the short connected, and believe me, I've heard actually of two situations where they left the short circuit connected and they energized the transformer. So You want to be as safe as possible with the type of instrument you use, with the type of connections you do. So there's another technique. It's a novel technique that you uh, can energize the secondary side of the transformer, and you perform the short circuit on the primary side, and you perform it through the instrument, not on the actual terminal. So with the regular same connection that you do for turns ratio, let's say you were running turns ratio with these in this transformer, the same instrument, the same leads, you just run the different the different test setting, and it will run the short circuit impedance. And we also have more information on this if you want to learn more about it. As I said, this is just like highlights. And you need less power, no shortings, and it's extremely accurate. And I said novel technique, but really this test has been done. If you think about sweep frequency response, when you do the short circuit test connection, it is still doing it from the high side, but the short and the voltage level is already the same, or probably around the same area that is being used. So it basically using that concept and applying that in a new instrument, in a new uh, uh, way to run the test. Then to finalize about the presentation, the turns ratio test. So why to mention this for these distribution in dry type transformers? Well, we know that the error, the limit error for turns ratio is 0.5%. Whatever result you get, it should be below the 0.5% of the nameplate ratio. And again, as I mentioned before, you might get a high error, 0.55, 0.56, or zero point 0.7. And well, I already mentioned these transformers are not as efficient, and they might not be high quality if they are not required to be like that. And that for different reasons, they might end up being voltage dependent. What this means that for you to get a good result, you need to use a voltage higher than the typical voltage that you will find in regular turns ratio testers. So in this case, you can see here in this graph a test that is performed on the same transformer, the same phase, at 8 volts, 40 volts, 80 volts, and 125 volts. You can see very easily how the result improves as you increase the voltage. This is the voltage dependence that I'm talking. The transformer is good. There's nothing bad with the transformer, but it has a voltage dependence. Now, there are different things that you can do, or basically raising or increasing the voltage increases the flux that you have in the transformer. So now you have more flux and the transformer can do its job better. Take that flux and convert it into a different voltage on the other side. So that's what you want to have, higher flux inside the transformer. You can use a higher voltage, as I already mentioned, or you can energize the 3 phases at the same time. And that's why I mentioned through 3-phase ratio meter before. Having the 3 phases energized at the same time, it's giving you flux of 3 phases, and that definitely is going to have, of course, more flux inside the transformer. And the other technique that you can use is to step up to use what it's called the step up technique. Typical modern instruments do the test from the high voltage side. They apply voltage on the high voltage side, and then the induced voltage is measured, of course, on the secondary or the tertiary winding. And voltage dependence is also very typical in transformers with tertiary winding. So instead of doing that, energizing from the high side, you want to energize from the low voltage side. That is called the step-up technique. And you can see here, testing the same transformer, or testing a transformer, the 3 phases of the transformer with a step down 80 volts. And in blue, you can see step up with 8 volts. So much lower voltage, but using or testing the transformer from the low voltage side. And And then if you add to that step up, if you add the three phase, you also see a big difference. You can see here in green the results from a step up three phase test. So the three phases were tested at the same time. And this is just showing one phase, but it's three phases. You can see that the voltage is extremely low, and compared to a step up single phase, the error is much better. So you get higher accuracy with this technique, and if you are in that transformer that has that voltage dependence, the transformer is going to pass. One last thing about the turns ratio. You might test with the step up, or you might test with higher voltage, you might test with the three phase instrument, and you still get a result that is higher than 0.5%. Well, um, everything is about the turns, and for the ratio to be exact, the number of turns, or the turns and a fraction inside the transformer, they need to be exact. And if the transformer doesn't have the quality, or because it is normal to run the let's say you have a Y connected transformer, and your neutral point, you're going to have it in the one, like on the left side of the transformer. Your phase A, which is on the right side, or sorry, on your C phase, which is on the right side, it's going to have a longer conductor, and it's going to affect your winding resistance, and it might affect your turns ratio. So in those cases, the same standard C571200 allows for that. And they just mentioned, they have a note there, and I put it here, that if you need to check the volts per turn, and do a check of that ratio of that error. And if the volts per turn is higher than 0.5, then it is accepted for the transformer to be higher on the actual turns ratio. And basically, they are recommending for you to round to the nearest turn. That's what it actually says. You can round the ratio to the nearest turn. So if you're going to find or encounter transformers that have that characteristic, that they're not going to pass the 0.5 criteria. I went a little bit over my time. My summary about this presentation is that you need to understand the transformer that you're going to be testing, nameplate information, manuals for the transformer are very important if you want to troubleshoot, or if you want to be well prepared. The other highlight or part of this presentation is that some tests may not be able to be performed. You might not be able to do some of the insulation tests, or you might not be able to have access to a certain part of the transformer, and you're not going to be able to run tests. Or you need to leave just with some of the tests that you wanted to run. You might need accessories. You might need also different techniques. If you want to expedite your assessment on power factor, you may want to use the 1 hertz because it is of a higher sensitivity. You may want to use a 3-phase tester to be able to get away of that voltage dependence and get good results, or more accurate results. Short circuit impedance is a test that it's very good test, but it's not commonly used. And we think the culprit of not using that test is the difficulty to run the short and the need for a powerful source. So if you change to a technique that you don't need to do an external short, that you can do the short with the leads through the instrument, and test from the low voltage side, it's going to give you a lot of value in your maintenance procedures. And for winding resistance, you may want to have an instrument that has higher current and has dual source, or use the dual winding injection technique. With this, and before we move into the questions, of course, we want to show you our solutions related to transformer testing, and we have many more solutions for transformer testing, but I wanted to put here in this slide what we think that will be a good toolbox for different situations. So, for example, this on the left side will give you insulation assessment, turns ratio, short circuit impedance, and winding resistance. S1 or MIT will give you the insulation resistance test. TTRU1 will give you the turns ratio and the short circuit impedance, and MTO 106 will give you the winding resistance. Very good set of tools for small transformers, dry type, especially because of the insulation testing. Now, if you do kind of a mix and you go a little bit into the high side of the MVAs or the medium size of the MVAs, and also do distribution transformers, oil immersed, dry type, then and you want to have everything in one single box, you have the tracks, which is a multifunction test set, and it not only does transformers, it does circuit breakers as well. It's an instrument that has an excellent manual interface that you can use for troubleshooting purposes. And then if you prefer the discrete instruments or individual instruments for different tests, then you have a combo that you can do with the Delta 4000 for power factor testing and do the 1 hertz test. TTRU3, which is a true three-phase instrument, will do the step up. And then you have MTO 200 family that will do your winding resistance with dual winding injection. So with this, Michael, we are ready to move on to questions.
Perfect. So as Volney mentioned, our presentation portion of our webinar has concluded, and we'll take some time to answer as many of your questions as we have time for. If you have any questions, please submit them now into the Ask a Question window on the left side of your screen. For those of you who are leaving, if you could, please be sure to fill out our survey before heading out. We would greatly appreciate it if you could take a couple of minutes to fill out that form and let us know how we can continue to improve upon our webinar series. On that survey, there's also an area for you to request a quote or a demo on any of the products that Volney just ran through. As a reminder, a copy of your presentation, certificate of attendance, and a link to the recording of this webinar will be available in 2 business days. The link used to join this session will actually bring you into the recording of this webinar a couple hours after we wrap up here today. If you'd like to join us in person later this year to discuss innovations and advancements in power transformers, you can check out Mega Power Grid Summit 2024 in the banner on the bottom of the screen, or by visiting it at megapowergrid.com. You can view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.mega.com/webinars. And be sure to register for our next webinar on April 19th, titled Dissolved Gas Analysis and Oil Quality, How to Test Oil and Diagnose Equipment Health. That will be presented by Tom Cleaver. All right, now that we've got through all of that, let's jump into the questions. The first one I have, I'm going to direct over to our panelist, Joseph Aguirre. Joe, Slide 8 mentioned power factor arrestor test form. Can you elaborate on this recommended test?
Yes. So basically all you're doing is power factoring your lightning arrestors, and the reason for this is just it reveals certain conditions of the actual lightning arrestor over time, because the purpose of the lightning arrestor is to take any over potential, any transient voltages that are coming down your line, typically due to lightning strikes or switching, and dissipating those safely to ground. So you typically have metal oxide arrestors, silicon carbide, where you may have just a spill gap arrestor. So majority of these testing standards are for your MOVs or your SIC type lightning arrestors. And like I said, you can see different things inside these, such as moisture deposits, different kinds of corrosion. If there is a crack in the porcelain that's not all the way chipped off, it can have a higher watts loss on that one as well. Different open shunts within the varistors inside internally, and defective gaps such as those. So that way, while it's in service, you know that it's not going to fail.
While I have you, I'm going to throw the next question over to you. Is it a good idea to perform a non-destructive full load test on a brand new 4160/480 volt transformer?
Okay, so it depending on your manufacturer, some manufacturers do recommend to do a full load test, or it could be part of the SOP, part of a just a commissioning test of the actual transformer. The reason why you would like to do this, if you could do this, basically load banking your transformer, putting full load on the primary and the secondary winding, is because you're reassuring whatever you purchased can pretty much handle these temperatures that you want. So you'll have a temperature rise stamped on your transformer, either 55, 65, can be 75, 85, depending on your geographical location. So what you're really doing is looking at that true efficiency of your transformer and kind of that voltage regulation of the transformer while you're doing so. And then also you can make sure that there's not anything loose or damaged within the transformer as you're load banking from 25, 50, 75, 100% load on your transformers by performing hotspot tests as well.
Thanks, Joe. Going back over to Volney, our dried transformer has been ideal for a few years. Hot on the primary, but never closed on the secondary. Breaker is closed on the primary, being 13.8 volts, and open breaker on the secondary, 480 volt. My question is, if we close the breaker on the secondary load, should I worry since the transformer has been ideal for a few years? What should I pay attention to when I do tests and maintenance?
Okay, well, I guess I need to assume a couple of things or clarify a couple of things from the question. When it says hot on the primary, I would refer to this that the transformer is being soaked. So it's energized, it's actually energized, it's inducing on the secondary side, but it's not delivering current. I guess it's a backup transformer, probably a critical facility or something like that. So it's ready to deliver current, and but it's not doing so. So and when the question says that it's been ideal for a few years, I am assuming that periodic maintenance is being performed, or that's what I would think that this being ideal refers to. If it's not, or basically the question is, what should you do? Well, being a transformer that is it's just sitting there soaked, I guess also it might be under a good temperature condition, so it might not be accumulating moisture. Of course, dust might be accumulating dust, or other contamination, depending on what's the enclosure. So it's a lot of depends, or a lot of assumptions here. But the main thing that I will focus on would be the insulation, like a sanity check with an insulation test every now and then will be perfect. Using the step voltage will be another good thing to incorporate there, so you can see if there's any change in the different results at different voltages. That will be my primary recommendation for this transformer.
Thanks, Foley. Going over to our next question, Joseph. What are your thoughts on partial discharge testing on a liquid-filled transformer if you suspect partial discharge? And are there any other tests that can be ran to disprove?
Yes. So I would highly recommend partial discharge if you're suspecting partial discharge, or if it is a critical line, you can do online monitoring while you're doing so. You can also utilize online gas monitoring as well, because whenever you're having partial discharges within the transformer, it's going to produce hydrogen. And so as you're running a DGA test, or online, as it's running an online DGA test as well, you'll see starting creeping just in the hydrogen realm. You can notify this on you can notice this on a Duval triangle, is typically the top of the Duval. And if there is anything other than that, and so let's say there's low energy discharges or small sparking caused from the PD, so the PD is actually growing a little bit, you'll notice that on the D1 scale of your Duval triangle, and the different gases that are produced by the different heat, you can kind of say, hey, this is partial discharge, and it's growing into something else. And while you're also online, you can use your ultra high frequency sensors, and you can use acoustics to actually kind of pinpoint where in the transformer that it's closest to. So whenever you can de-energize and do a actual internal check and go inside and look for it, then you can kind of narrow down where you don't need to look.
Thanks, Joe. Back over to Volney. Volney, what does ISO fuse stand for in the PMT nameplate? Current limiting fuse? Is the isolation link fused the bayonet fuse or the CLF?
Okay, let me bring this slide back. So the ISO stands for, I think it was this. So, and this one, let me see what slide, PM nameplate, okay. So yes, ISO stands for isolation link. And now this configuration, as you can see in this diagram, we don't have the current limiting fuses. You could have the situation that you don't have the isolation link, or you don't have the fuses, but you may have the isolation link. So it is a matter of understanding and knowing that the transformer from the nameplate. And you can see here, you can see in this slide, you have the isolation link, the bayonet fuse. So it's different situations, different configurations that you will have, and it's a matter of looking at the manual to be able to understand what you have.
Thanks, Volney. While I have you, this next question is also going to go to you. Is it necessary to perform a polarity index test on a liquid-filled transformer?
That's a very good question, interesting question, because it is normal to do that. So, and there's a note in one of those documents, I do not recall exactly right now which one, but there's a note about the polarization index on liquid immersed transformers. So polarization, what you're trying to do when you run an insulation test is depending on the type of insulation, how it is, the molecule structure, that level of the composition of the insulation, you might have molecules that polarize or do not polarize. So when you run the test on a cable, or sorry, on a motor or a dry type transformer, the dry type insulation polarizes, and that will demand certain amount of current. And at certain point, that current kind of reduces and it disappears almost from the test, and you are only left with the leakage current. Oil, in an oil immerse, you have paper and you have oil. Oil does not polarize. It does not have the polarizing agent. So you are not going to get a very good polarization index result on an oil immersed transformer. Is always going to be somewhere in between 1 and 1.5, I would say. But it's never going to be close to 2, as you would expect from the theory and from other insulations. And however, so that's the first thing to consider, that the result is not going to be that good. And if the result is too good, well, that tells you that if the polarization index is close to 2 or high, then that tells you that there's something in your insulation that is being polarized and should not be being polarized. So there's a note there that you need to be careful with the polarization index on oil immersed transformers. You can run it, but it's a matter of understanding very well what you're doing, what type of result you're getting.
Thanks, Foley. Throwing things over to, I guess this one is once again over to you, Volney. Should we do a dissipation factor test for SAT? If yes, how do we carry out that test?
Okay, so, well, dissipation factor is the same term for power factor testing. SAT is site acceptance test. So that's definitely a test to perform. Power factor, we always refer to as power factor, and I mentioned several times leakage current related to power factor, but it's also a mechanical test. Let me go back to the first, the C-grade slide, and you can see that for magnetic, there was something related to mechanical condition, and both the leakage reactance and capacitance are related, are recommended for winding geometry. So when you do power factor test, you get an indication of the mechanical condition of the transformer. Again, capacitance should not change if nothing mechanically changes inside the transformer. So because you are accepting the transformer, that will be one of the easiest ways or quickest way to identify if the transformer had a deformation during transportation or even through after a fault. That's a very good test to perform.
Thanks, Folney. Now back over to Joe. Joe, is there an order that any test should be performed?
So typically when I was in the field, the first thing I would do would be insulation resistance or a Megger test. And that is just a quick go, no-go test, because typically if it'll fail your insulation resistance test, either high to low or low to ground or high to ground, then you're very limited on what other tests you can perform. So, and this is also the state of your transformer, because if you, let's say you take it out of service and you do not short the sides and short them to ground, so high to ground, low to ground, the transformer is just basically a big capacitor. So you're going to have stored induction in there, which is going to magnetize your transformer as well. So if you did go up and start power factor first, you may have, depending on the voltage that you use for like TTR and excitation, your numbers may be skewed on those. So whenever you say, is there a best practice on how you do it all situational? So if you went in and de-energized a transformer, you grounded it, isolated it, you're starting testing today, I would recommend insulation resistance test set testing, then perform all your testing with power factor. So that is your overall, your C1, C2s, if applicable, excitation as well, TTR, winding resistance, then DMAG at the end. However, if it was a situation where it might have been sitting there stagnant for a day or two or three, maybe even a couple of weeks while the winding's not shorted to ground or the bushing's not shorted to ground, the first thing I would do personally would be the winding resistance test, DMAG it, then you can continue with all your AC tests.
All right, thanks a lot. Back over to Volney. Volney, if you have damage or cracks on the epoxic insulation which covers the coils, which measure do you recommend? PF, PD, in order to evaluate or measure the damage?
Okay, I see this question is from my friend Gerardo. Nice to see you're here, Gerardo. Of course, we're talking about dry type, and you have access to a visual inspection. You can probably determine a couple of things easily, at least from the exterior walls. And the power factor would be probably the best, the first thing. It's a quick test, an easy test to perform. And with power factor or dissipation factor, what I would recommend definitely is doing the tip-up test, the increasing the voltage. Like if it is probably, let's say it's 13.8 or a little bit higher, you can go up to 10 kV or 7 kV and do steps of 1 kilovolt and do 7 steps. Power factor should not be too different from the 1 kilovolt test to the 7 kilovolt test. The difference between power factors should not be higher than 0.5, or you should not see a kind of a very steep increase after a certain voltage. If there's an increase, it should be a little bit linear and not too steep. When the other question about partial discharge was asked before, I wanted also to mention that partial discharge it's a very important test for dry type transformers. You're going to see prescribed that test in the guides for the dry type transformers that I mentioned for factory purposes. And well, now with all the equipment that you have accessible for partial discharges, that you can do it easily in the field, then I would recommend, if it is a critical transformer or if it is something that depends on a very good assessment, I will definitely add the partial discharge to that.
Thanks, Folney. I'm going to kick one more question over to you. What is the maximum current that the mega transformer ohmmeter can supply? The MTO 106 shows only 6 amps. Is there an instrument with higher current output?
Oh, yes. So as I said, this in the slide, I just showed the MTO 106 because that's a very small portable instrument. And in that package, I put it together there, that group of instruments. I put them there because thinking on the renewables applications where you have difficult access and you want to move around very easy from side to side. And yes, it has only up to 6 amps. We have instruments that go up to 10 amps. We have another instrument like the tracks that I'm showing here goes up to, it can go up to 100 amps, but for winding resistance, it can do continuously up to 75. And then the MTO family has up to, it has an instrument that can go up to 10 amps and another one that can go up to 50 amps. And we have another instrument that I'm not showing here that has the dual source, and it can go up to 32 amps on low voltage side and 16 amps on the high voltage side. So we have options is what we have for you.
All right, thanks, Volney, for that one. And I think we have time for one last question. I'm going to kick it over to Joe. Joe, which acceptance test would you suggest performing on a transformer before shipping it on site?
All right, so this, I would consider this like an on-cart test. So this is basically before you accept it and set it on the pad before you start doing acceptance testing. So whenever you're doing an on-cart, or what I have done in the past, is first thing that we'll do is the insulation resistance test or a mega test, just to make sure everything checks out. We would also perform we would perform a TTR on the as-found tap and an overall power factor, and then as well as an SFRA if applicable. And then you could compare the SFRA from whenever they shipped it. So it should be, depending on the transformer, sometimes they will not have the bushings in there, and they will have caps on top with leads sticking out where you can do tests. And then they'll have a fully assembled SFRA, and then they would have one before they shipped SFRA. And so now you can compare the before shipped SFRA to the on-cart one. And then once you assemble it and put in the bushings, and then that's when you're going to compare the two from the as assembled to the full acceptance testing SFRA. So those would be the minimum tests that you would perform on acceptance on cart testing.
Thanks, Joe. Oh, and thanks, Volney, for that matter, for putting on our presentation today. As we conclude our webinar here, I'd like to remind everyone to please fill out our survey so we can continue to improve upon our future webinars. We'll also have a copy of this presentation, your certificate of attendance, and a link to the video recording of the webinar emailed to you in about 2 business days, usually a lot sooner than that. I'd like to thank you all once again for attending today. I know we have many options out there on how to spend your Friday morning, and we appreciate you spending it here with us. But I'll leave it with that. Thank you to our presenters and you, our audience, for joining us. We'll be back here next month with another Testing Tactics webinar series. And again, feel free to check out our Mega Power Grid Summit 2024, which is happening this November, where you'll be able to see our presenters here and a number of our other industry leaders talking about our power transformer innovations and upcoming changes in the industry. But with that, I'll let everyone enjoy the rest of their Friday. Hopefully your weekend is restful, and I'll see you again on here soon. Bye, guys.
Thank you. Bye-bye.